Hi everyone. Uh, Today I am going to give a talk on our paper, which is accepted in CCGrid 2021 conference, automating conflict detection and mitigation in large-scale IoT system. So first, let me introduce myself. Myself, Pavana Pradeep. I am a research assistant under Dr. Krishnakant in Temple University, Philadelphia, USA. My co-authors are Dr. Mitangshu Pal and Dr. Krishnakant. In this talk, I'm going to give an overview on our paper, where we have developed a mechanism to automatically identify and resolve conflict in an IoT system. Our approach ensures that safety properties are satisfied, and we have developed a look-ahead mechanism to identify potential events and resolve the conflict via an intelligent combinatorial optimization-based approach. So the emerging edge computing systems define a three-layer model. Lowest level is the device level, which consists of multiple clusters of IoT devices, each generating continuous data streams. Middle level is edge controller, also termed as edge gateway, with one edge controller per device cluster that provides online analytics and query processing based on the data streams received by the devices. Finally, top layer is the backend cloud that provides offline analytics and archival storage of data collected by edge computing systems. These systems are inherently multi-party with involvement of multiple vendors at every level, including devices, edge controllers, virtualization layer, and higher level services. This paper considers IoT system in the larger context of edge computing systems as well. So, what is the problem that we are trying to solve? So we know that complex IoT systems supporting multiple services, particularly the edge computing system, as I told, consists of multiple subsystems, each designed, installed, or managed by different vendor, organization, or a party. In particular, each physical cluster of devices or the services offered on top of these clusters may form an independent subsystem. Then each subsystem would have its own independent controller that has very little knowledge or access to the data or resources provided by other subsystem. Yet all these subsystems typically operate in the same shared space and thus are affected by environment and the actions taken by the other controllers. So hence maintaining a safe and secure operation in such multi-party system becomes quite challenging because of lack of coordination across such independent subsystems, lack of visibility to generated sensor data streams in a timely manner, and inability to perform requests or even be aware of the actuation by other parties. So this forms the main motivation for our research. So what's our vision? We consider a system of subsystem where each subsystem has its own set of operational rules designed not to conflict with one another. However, conflicts can arise across subsystems. The proper operation of the entire system is defined by a set of safety properties that essentially take the same form as operational rules. The inability to satisfy simultaneously both safety properties and operational rules is considered as a conflict, which is given by unsatisfiability. Since the safety property is a necessary condition, one possible way to avoid conflict is weakening the conflicting rules. So then what is weakening? So this weakening is possible in most cases because the rules involve some threshold, like for example, if temperature is greater than 75°F, then open the windows. Or the rules can involve time periods. For example, if the time is between 10 a.m. to 5 p.m., then turn off the lights. So the idea is that if these thresholds or times are altered, then the conflicts can be avoided rather than having to block one of the conflicting actions. We explore intermediate situations where we look ahead by some time duration and examine the likely events based on the current conditions. We could then resolve them proactively by changing the threshold and duration. In addition to the generic approach, we are faced with some challenges like both operational rules and safety properties involve time and how we model time or temporal component. So what is the approach that we are using to check the satisfiability efficiently? And finally, what's the strategy to weaken these operational rules? I'll discuss one by one into these questions and how we addressed each one of them. Before getting into detail, let's see how we are modeling events and actions. So we know that an event will invariably involve some thresholds and some time periods, as I already mentioned, and types of actuation involves either unlocking or opening a door or putting off an alarm, etc. So hence we model the IoT system as a finite state machine such that detecting and resolving a conflict can be reduced to a property checking problem on this finite state machine, which and this problem can be solved using any existing model checker. The finite state machine can be seen as a directed graph where the device states and the operational rules correspond to the state and transitions respectively. And the state can be represented using value of features or attributes of each device. For example, a thermometer may have a pair of attributes, namely time and temperature, where the temperature reflects the value measured at the specific time. An operational policy is expressed as a first order logic that essentially moves the subsystem from one state to another. This policy can be expressed as a triple having the precondition and the postcondition assertions about the state before and after taking the stated action I. The pre or post conditions are Boolean expression or state variable, including status of an actuator, sensor values. In many cases, the Boolean expression could be just a simple comparison of state variable. For example, door camera is equal to on. A safety property expresses the idea that something bad should not happen during the system execution. An example of a safety property could be like if some smoke is detected, then open windows. Hence, this safety property provide a generic way of stating what is considered to be a conflict. Since we assume that no conflicts occur within a subsystem, the safety property necessarily go across multiple subsystems. So how are we modeling these temporal properties? We in our paper, we are using a well-known temporal logic specification called linear temporal logic, which allows the expression of concepts like eventually, until, as long as, sometime, etc. LTL formula are built upon some atomic propositions with some operators like and the logical operator, negation, and, or, etc. And it has some temporal operators like always, next, until, eventually, and so on. For convenience, we define time slots of a few different duration to represent events at different time scales. So this is a table that shows some examples of rules and safety property. We have many rules and safety property in our system. For convenience, I have not shown each one of them. So our system basically comprises of 5 controllers: light, fire, climate, security, and surveillance, running their own dedicated services. Example of an operational rule for a fire controller should be like once the sprinkler is on, turn off the sprinkler after 4 to 6 minutes. So why these time durations are important? Because without these time durations, the system may go into an infinite loop. So one example of safety property could be like when the sprinkler is on for 3 minutes, then the water valve is off. So this slide shows a representation of how we have represented our operational rules and safety properties using LTL. So as I already told you, LTL provides some operators like until, eventually, next, and so on. So here the operator X is used for the next step where the atomic proposition is true at the next time slot. The until operator can denote that if our atomic proposition is true at some point, then another atomic proposition is true until that time. Eventually ensures that any atomic proposition will be true eventually in the future. So the table shows the LTL forms of rules and safety property, which uses the operators as discussed. So how are you going to solve these LTL models? So as I told, the conflict between the safety properties and operational rules is termed as a conflict, and which is a Boolean satisfiability problem given in a first order logic. Still, with significant extension, since both safety properties and operational rules involve at least the comparisons and arithmetic, we need to include the appropriate theory to deal with them. This is the domain of satisfiability modulo theories. So as we know, this SMT theories can solve huge problems in real time, and thus the model checking amounts to checking whether the finite state machine is a model of the property to be checked or not. However, LTL does not deal with real time, which is crucial for expressing the operations in an evolving cyber physical system. We address this by making the time slotted. One could then speak of next or previous time slots. With this, SMT itself need to be extended, and we use the existing NUXMV model checker. So there is a whole lot of advantages of using this model checker. The NUXME model checker uses binary decision diagrams and SAT-based model checking, and it addresses the problem of state space explosion, which are often arises in a finite state machine problems. In case of unsatisfiability, it provides a counterexample that are useful in analyzing why and how the conflict has happened. So what is our approach? So our approach is a combinatorial optimization based approach. We use this approach to bring minimum changes to the rules and make them conflict free. We first pass the rules through a maxsat solver, which returns an unsat core in case of conflicts. The unsat core consists of rules and conflicting rules and safety properties. The next step is to find ways of weakening these rules. These methods move essentially from one solution to the next while keeping track of the best solution found so far. So our problem is a constraint optimization problem where the constraint is the satisfiability of the altered formula. As we know that there are several methods in the literature, but but it's the best to use a method that attempts to balance between feasibility and optimality when moving around in the state space. One algorithm that works extremely well for high dimension problems is called dynamically dimension search, DDS, which initially perturbs most of the variables but perturbs fewer of them as the iterations proceed. So the key to finding near optimal solution quickly is the use of domain knowledge. The perturbation to the solution made at each state represents various correlation and dependency. Hence, domain knowledge of the system is important. Excuse me. Let's take some example to understand how we are going to resolve the conflicts. And we classify the conflicts into many different categories and how we are, what kind of perturbation of operation rules we have developed. So we will take a notation as shown in the slide, like for example, a controller C executing action A on actuator X, which results in an effect E that persists for some time slots. So this table gives the details on type of conflicts occurring in an IoT system and the way we are trying to mitigate conflicts. So for I'll give an example like type 1A conflict, which involves both energy and fire controller issuing commands to open and close doors in a short period of time. And the safety property says that door must be opened, must be closed within some time limit. This conflict can be resolved by making the threshold greater than the minimum threshold set so as to resolve the conflict. Now, based on the type of conflicts and knowing how to resolve, let's see how we have developed our epsilon DDS based algorithm, which is entirely based on domain knowledge. From the unsat core, we identify rules R prime that are directly or indirectly dependent on C. This dependency is expressed via dependency graph G, where the vertices denotes the rules and safety properties, and the directed edge denote the dependency between them. We then take transitive closure of this G prime using Floyd-Warshall algorithm. Thus, in G prime, an edge from I to J represents that J is directly or indirectly dependent on I. From this, we mark the vertices in C or neighbors, wherein we tune the parameters such as different threshold or time variable to eliminate the conflicts. We have also considered the type of conflicts that do not involve threshold or time variables. We resolve such conflicts by allowing the higher priority event to execute the action at runtime. For example, when a fire and safety controller issues command to open all the doors and windows, Simultaneously, due to drop in outside temperature, the climate controller gives command to close all doors and windows. Such a conflicting scenario does not involve any time or threshold. Hence, we give priority. Hence, the objective function of our epsilon DDS involves this both modified and unmodified variables, time durations, and all the clauses in our unset. We denote epsilon less than relationship between two solution. And intuition behind comparison is that if the solution x1 and x2 are feasible, or slightly feasible, or having the same sum of constraint violation, here the number of unsatisfied constraint in our case, then they are compared to the objective function value fx1, x2. Thus, in every iteration of epsilon DDS, the scheme identifies a set of j decision variables and includes them to the nx we perturb express according to equation in the line 11 while respecting the domain knowledge. So the right side figure shows the simulated scenario using home IO. For simplicity, we consider only two rooms in home, namely the kitchen and the living room, which have only 20 out of 112 various IoT devices. Why we used home IO? Because it provides a simplified model to simulate real-time heat transfer, including radiation, convection, conduction phenomena. Figure on the top shows our overall approach. The log file from the home IO provides detail of each event, timestamp, and the event's duration and the actions taken. It is then used for modeling interaction between devices and rules to build a finite state machine. The inputs to the model checker are rules and safety properties, and the transition system built from the log file. This finite state machine is verified against a model checker to identify the conflicts. In case of model checker finds some violation of safety properties, it provides a counterexample, which is the unsat clause, and which leads to property violation. So to evaluate the performance of our epsilon DDS, we implemented our algorithm, as I told, using home IO and using NUXMV. We start with a baseline of 50 operational rules and safety properties. The system includes, excuse me, 19 rules with perturbable thresholds. We consider 3 possible perturbations of each of these rules, thereby yielding a total of 57 different possible perturbations. Figure on the left shows the result that are averaged over 57 such cases. The x-axis indicates number of iteration needed by combinatorial optimization. It is limited to maximum of 200, where y-axis also shows the percentage of cases where algorithm could resolve the conflicts. It can be seen that our algorithm powered by domain knowledge can resolve the conflicts in all of the 100%, all of the cases in about 175 iterations. In contrast, normal DDS without any domain knowledge can fix only 53% out of test cases at 200 iterations. The result presented here shows the comparison of normal DDS and epsilon DDS in terms of processing time as number of rules increases. Notice that the y-axis is in log scale. Therefore, advantage for epsilon DDS in terms of speed is quite substantial. The result presented here shows the running time of our algorithm varies with the number of rules. For this, we consider 2 additional cases with 100 and 200 rules in addition to the original 50. Using the same scheme of perturbation and described in the previous slides, we have total of 57, 114, and 228 possible perturbation in all these 3 cases. The left y-axis corresponds to per iteration cost, which is seen to grow both with the fraction of perturbable rules and total number of rules. The growth is non-linear but relatively slow. Since our tests were carried out in a relatively modest test, we believe that our mechanism can quickly scale to thousands of rules with a well-equipped server. So in this paper, we have examined the problem of conflict detection and mitigation in large-scale IoT system by introducing notion of safety properties. And we allow both operational rules and safety properties to include time and temporal logic operations as an integral part. We allow the model to look ahead proactively to catch potential conflicts and mitigating them by temporarily perturbing the thresholds or duration in the rules. Such an approach offers more flexibility in dealing with conflicts than resolving the conflicts reactively by blocking or delaying one of the actions. We show our approach can resolve 100% of the cases. Thank you for listening. Have a good day.